Good day, everyone. First of all, I'd like to thank the Samahang Pisika ng Pilipinas for their kind invitation for me to share with you some of the things that we work on, especially non-Gaussian, non-Markovian stochastic processes. And I will be talking about those processes in the presence of an absorbing boundary or those that satisfy a Dirichlet boundary condition. So let's start with the type of fluctuations or random motion that we are going to deal with. Suppose we parameterize our random motion or fluctuations in this manner. So here we have a fluctuation. And in particular, let me represent the fluctuations in terms of an integral of this object. We have three functions here. We have a modulating function g, a memory function f, and a window function h. And this g, f, and h are all modifying the white noise random variable. And then we'll be integrating them from some initial time 0 to some final time t. The fluctuating variable x could represent many things. It could represent the positions of a probe particle in a complex fluid. It could be the fluctuations in geomagnetic fields. It could be the varying DNA distances in a genome, or it could be the daily cases, fluctuating daily cases in COVID-19. It could be the positions of a typhoon or the fluctuations in the rising atmospheric carbon dioxide level. So this is the type of environment or framework that we're going to work with. Now, this framework has been applied on several systems. This has been applied to an aging fibrine, and here we specify the memory function f, time window h, and the modulating function g. So for aging fibrine, it would have this form, and time window of this form, and just one for the modulating function g. And so on and so forth. With the studies on DNA, this would be our choice, with just 1 and 1 for the functions h and g. And for the study and the diffusion of proteins, we have these forms of the functions g, f, and h, and so on. So it has also been applied for studies on cyclones. And if you want to obtain fractional Brownian motion, which has a huge amount of application in the literature, then you just make the substitution for the memory function, for the time window h, and then for the modulating function. But so how do we proceed normally when we try to calculate the probability density function? So here we have parameterized our initial point plus fluctuations in this manner. And to solve for the probability density function, we first observe that the way we have parameterized our fluctuation, the initial point is fixed. It's at x sub naught. But then, since x sub naught plus fluctuations, the endpoint for these fluctuations at some final time capital T, for example, it could end anywhere. Okay, so we can have pictorially a configuration like this. So we start at some fixed point x naught at some initial time t sub naught, and it progresses in time. So this will be our time axis. This is the final time t. And at some final time t, the fluctuation could end somewhere here, it could end somewhere here, or it could end somewhere here. But suppose we want to pin down the endpoint. Suppose we want the final point at some final time capital T to be somewhere around x sub 1. We can actually pin down the final point at some final time capital T. So to pin down the endpoint at some, let's choose x1, at some final time t capital T, we can use the Dirac delta function, or if you have a fluctuating variable inside the Dirac delta function, they call this the Donsker delta function. And so this xt, if you remember, is just given by your initial point plus fluctuation, and it should end at x1. Now this Dirac delta function, as we all know, is always zero. The delta function is always zero except when the initial point plus fluctuation would end at this x1, then it spikes. The Dirac delta function lights up. Otherwise, outside of this situation, it's always equal to zero. So with the use of delta function to pin down the final point, we could have a configuration something like this. So at some final time t, all the paths that would contribute to our story are those that would end at some final point x1, and all the other paths would be zero. And to get the probability that this would happen, to get the expectation value or the probability density function, we have to sum over all contributing paths. So, and that's what we're going to do. But in particular, let's consider this situation. Suppose you have a fluctuation which starts at x naught, and it could go anywhere. This would be the allowed region. But then, if it hits a boundary, it is absorbed by this boundary, and so it can never go into this forbidden region, which is colored blue in the slide. So we ask ourselves the question: what then would be the probability density function, which would satisfy a stochastic process in the presence of an absorbing boundary, or it satisfies a Dirichlet boundary condition? That means the probability density function would vanish. It will be equal to zero once your final endpoint x1 is equal to xc, where xc is just the location of your boundary. Now, to solve this problem, we have to use the method of images to come up with a probability density function. So in the method of images, so we still have our usual path on the allowed region, but then we put an image point, the image point located at some 2xc minus x naught, which is actually just equidistant. It's equidistant for this x naught to xc, and xc to this 2x of c minus x naught. They're equal in distance, and we have this image point. So now we're talking about two paths. The original path in the allowed region, which we call xa, which is just your x naught plus fluctuation, and the path that originates from your image point. So a path from image point plus your fluctuation. So now let's use the Dirac delta function to pin this initial point plus fluctuation, pin it down to some x1. Let's say we want those two paths, the one from the image point and the one from the initial x naught, both paths ending at x1. So we use a combination of two Dirac delta functions, and let's call that L combination as some L. So we would now like to know the probability density function given this combination of two Dirac delta function. So all you have to do, since the delta functions are almost, well, zero most of the time, unless they end at some x1. So we sum over all these possible paths, and summation is actually an integration, and in particular we integrate over this L, or this combination of two delta functions, using a Gaussian white noise measure. You use a Gaussian white noise measure because inside this XA and inside this XB, as shown by this one, there's actually a Gaussian white noise variable, and you can only handle that if you do some integration using the Gaussian white noise variable. So okay, now to evaluate this integral over d mu, or the Gaussian white noise variable, our first step will be to express the delta function in terms of its Fourier representation, something like this. So whatever is inside the delta function, we exponentiate it for the first delta function. And for the second delta function, we also exponentiate it. So let's now write down the exponentiated form in the next page. So here we have the exponentiated form. We still have the integral over the Gaussian white noise measure at the end. But then we have the initial point plus fluctuation for the allowed region. And in the second exponential, second integral, we have the image point plus your fluctuation. So, so nothing fancy at this point. We just wrote down the delta function in terms of their Fourier representation. Now, we can actually factor out a common expression, exponential, this g integral of f and h on the second line, and the g times integral of f and h. And we could put it out of the integral because this is the only term which contains the Gaussian white noise variable. So we could actually carry out an integral over the Gaussian white noise variable. The terms in the third equation in this line does not contain any omega, or it does not contain any Gaussian white noise variable, so we could pull that out. And to evaluate this integral, we make use of the definition, or the definition of the Gaussian white noise measure, which is defined using a characteristic functional, and it's given like this. And the integral that we are concerned with is actually of this form. If you let k, g, f, and h be some psi, then the integral that we would like to perform is actually something like the left-hand side. And on the right-hand side is the result of the integration. It does not contain any omega anymore, but it's just an exponential integral of psi squared. So in the next page, you will just see an exponential integral of psi squared, where your psi is given by k, g, and h. And we have to square that. And that would be the result of the integral over d mu. So now here we have the result of the integral over d mu. This is psi squared, k squared, g squared, f and h squared, which is outside of these two exponentials. Now what we can do next in order to make things clearer is to multiply this exponential into the ones inside this curly bracket. Okay, so if you do that, then we have two integrals, integration over this and integration over this, and putting in the result of the d mu integration. This is the result of the d mu integration. We have now placed it inside the curly bracket, and you can clearly see that the first integral is just a Gaussian integral of exponential of k squared dk, and we can make use of this expression, which is available in the table of integrals. And the second integral is in the same situation, k exponential of k squared dk. So quickly you can make use of this integral and everything would simplify. And in fact, the final result, because now there's only the integral over dk left, the final result can be written in this form, where this m in the exponential and this m in the coefficient is in terms of the functions g, f, and h. Now remember that we have not yet specified the specific form of g, f, and h. They are determined once you have studied a specific physical system. And so now you observe that suppose your x1, your final point at some final time t, hits the boundary at xc. So if you let x1 be equal to xc, then this will be xc minus x naught, and this would be x1 will become xc. So this whole thing would also become xc minus x naught. So these two exponentials would have the same form, and with the minus sign, it becomes 0. So at x1 equal to xz, the whole probability density function becomes 0. So this is the right PDF, which would describe a non-Markovian Gaussian stochastic process in the presence of an absorbing boundary. And in fact, there are a huge amount of possible values of the f and h, and this is as a sample. I quickly go through this because in the coefficient we have this thing. So these are the possible choices which you can choose from when you're studying a specific physical system. So thank you very much for listening.
I am Edward Aris Fajardo from MSc Marawi. I'll be talking about effective dynamics of 2D black electrons in external fields derived from symmetry. This is based on a paper of the same title um, published in Physical Review B and done in collaboration with my PhD advisor, Roland Winkler. Two-dimensional materials are materials that exist in layers. They can be placed on top of each other, just like the Lego in the figure. The discovery of graphene led to an increase in studies of other two-dimensional materials such as silicene, boronitride, transition metal dechalcogenides, including tungsten diselenide, molybdenum disulfide, whose crystal structure is shown in the figure. The theory that I'll be discussing is applicable to any material, but for illustration purposes, I'll focus on molybdenum disulfide. In crystalline solids, the atomic positions can be generated by applying a translation of the atomic positions at the unit cell by integer multiples of the basic vectors A1 and A2. This can be described by a Schrödinger equation of periodic potential, whose solutions are block functions consisting of plane wave and function periodic in a function in terms of a function of the energy in terms of this coefficient k is called the band structure, and for molybdenum disulfide, this is the band structure where we label the highly symmetric points of the Brillouin zone gamma, m, and k. This can be analyzed using the symmetry of the crystalline solid. So we'll review a little bit about group theory by looking at the symmetry group of the equilateral triangle C3V, whose elements are symmetry operations that keep this triangle fixed, such as identity, 120 degrees rotation, a counterclockwise rotation, its inverse, C3 inverse, and vertical reflections along axis 1, 2, and 3. For example, the ammonia molecule is characterized by this symmetry. The result of successive applications of uh, two elements in this group is summarized in a multiplication table. For example, if you have C3 applied twice, you get C3 inverse. These elements can be represented by matrices as long as they obey the group multiplication table. And the smallest matrices that we find are called irreducible representations. For example, for C3V, the IRs are irreducible representations are gamma 1, or the identity representation where each element is represented by 1. We have gamma 2, where the identity and the rotations are each represented by 1, and vertical reflections by -1. And gamma 3, which are two-dimensional rotation and reflection matrices. Functions can also transform. So if we apply a symmetric transformation on f of r, that is just equal to f of the transform r. There are also functions transforming according to IRs. For example, z transforms according to gamma 1. LZ, or the z component of angular momentum, transforms as gamma 2 because it changes sign under a vertical reflection. And x, y are the basis functions of these two-dimensional matrices. In a Hamiltonian, the eigenstates transform according to IRs of the symmetry group. Also, the degeneracies are indicated by the dimensionality of IRs. In a book by Wigner, he mentioned that the representation of the group of the Schrödinger equation, which belongs to a particular eigenvalue, is uniquely determined up to a similarity transformation. However, we will see later that the coordinate system actually matters. If you want to study the dynamics close to the band extrema, we can make use of the effective mass approximation, where we use the Hamiltonian of a free electron but with a modified mass. To include the effects of electric and magnetic fields, we can replace the momentum by the crystal momentum P minus EA, where A is the vector potential, and then add the Hamiltonian with the scalar potential. Certain details of the Hamiltonian depend on the IRs of the bands, so our goal is to identify the IRs characterizing the bands. This is relevant in invariant expansion of Hamiltonian and also in optical selection rules. So for the main part of my talk, let's discuss about symmetry analysis of tight binding block functions. We start with a tight binding basis phi at a position r. This is equal to a plane wave term plus times a term or a function containing atomic orbitals phi. R J labels the unit cell. Capital letter R is the atomic position. W is our Vikov positions or Vikov letter. Mu runs from 1 to m, where m is the multiplicity of the Vikov letter. For example, for MOS2, MO has a multiplicity 1, S has multiplicity 2 corresponding to the top and bottom sulfur atoms. Our goal is to decompose the representation for our tight binding bases into IRs. We do that by considering the region near the atomic position R. What we get is a plane wave term Q times a term proportional to the atomic orbital. So the symmetry is that, or the representation is just equal to the representation of Q times the representation of the atomic orbital phi. For atomic orbitals, we can get symmetrized atomic orbitals that transform like IRs of the group of the wave vector. We can get them, we can derive them using a projection operator. Now let's have an example. Consider p orbitals in molybdenum disulfide at the gamma point characterized by the point group D through H, which has the symmetry or characterizing the symmetry of a triangular prism. In this case, the p orbitals decompose into twofold degenerate px and py orbitals, transforming according to gamma 6, and pz orbitals according to gamma 4. At the K point here, this is characterized by C through H, or the symmetry of a triangular prism with half of each side shaded. P orbitals decompose into non-degenerate px plus ipy, px minus ipy, and pz orbitals, transforming according to gamma 2, gamma 3, and gamma 4. This result is valid for any crystal as long as, or if you have group of the wave vectors D through H and C through H, for example, single and tri-layer graphene respectively. This means that the symmetry of the atomic orbitals are independent of the location of the atom. Now let's consider transformation of the plane waves. If you apply a symmetry transformation on a plane wave Q, this is just equal to the plane wave at the transform position GR. For example, if you have RJ applying a 120 degrees counterclockwise rotation, that gives us RJ prime, where Rj prime is just equal to Rj plus a vector. So we can write a transformed plane wave by the plane wave at the original unit cell times a phase factor we call D, or this is our representation D. There are two possible cases. One when the Vikov position has multiplicity m equals 1, and in this case, D is irreducible, and the plane waves transform as one-dimensional IRs. In the second case, we have Vikov positions with multiplicity m greater than 1, such as sulfur atoms in MOS2. In this case, we project on IRs. Now let's consider the plane waves, the symmetry adapted plane waves at the gamma point, characterized by D through H. Plane wave at molybdenum atom transforms as gamma 1. At sulfur atoms, transform as gamma 1 and gamma 4. MOS2 can be described by three coordinate systems. One when the origin is at the center of the hexagon. Another one with the origin at the molybdenum atom. And a third one when the origin is at in between two sulfur top and bottom atoms. So the plane waves at K point, characterized by C through H in coordinate system A, at the molybdenum atom transforms as gamma 2, at sulfur atoms, gamma 3, and gamma 6. Now, if we go to coordinate system B, it becomes gamma 1 for molybdenum atom, gamma 2 and 5 for sulfur atoms. And in coordinate system C, we get gamma 3 on molybdenum atom and gamma 1 and 4 for sulfur atoms. Let's see how this change in coordinate system results in a change of the IRs. If we go back to coordinate system A, applying a translation corresponding to this vector tau, we get coordinate system B. From B, we apply the same translation vector, we get coordinate system C. And from C, applying that again, we go back to coordinate system A. Vector tau is given by this expression. For an eigenfunction transforming according to gamma I, in a translated coordinate system, it will transform as gamma I prime equals to gamma tau times gamma I. This gamma tau is given by this expression related to this vector tau. For MOS2, this gamma tau is equal to gamma 3. So if you have in coordinate system A states transforming as gamma 1, 2, 3, 4, 5, and 6, it becomes gamma 3, 1, 2, 6, 4, and 5 in coordinate system B, and will become gamma 2, 3, 1, 5, 6, 4 in coordinate system C. We see a rearrangement of the IRs as we go from one coordinate system to another, so we call this the rearrangement representation. Now, if you have a general Hamiltonian, we can write this in a block diagonal form if you use a symmetrized basis. Each block corresponds to states transforming according to the same irreducible representation. For MOS2, at the K point, uh, the Hamiltonian is diagonal. And if we consider the point close to the K point, we see a coupling on states transforming according to gamma 1, 2, and 3, and coupling on states transforming according to gamma 4, 5, and 6. And finally, to include the effects of electric and magnetic fields, we can make use of the envelope function approximation. As a summary, we have developed a general theory to identify the block state IR. This has been applied to MOS2, single layer, bilayer, and tri-layer graphene. We did that by decomposing the tight binding bases into plane waves and atomic orbitals so that the IR of the tight binding block state is the plane wave IR and the atomic orbital IR. We also have seen that the shift in coordinate system produces rearrangement of IRs. However, for the analysis show that the Hamiltonian is not affected. Also, we have seen how symmetrized block states produce block diagonal Hamiltonian.
Good afternoon. Today, I will be sharing with you some of our results on quantization of time of arrival functions. In this discussion, we will be focusing on the two specific orderings, symmetric and Born-Jordan orderings. Here is the flow of my presentation. It is composed of 4 sections: introduction, symmetric ordering, Born-Jordan ordering, and our conclusions. Equation 1 presents the formalism of the generalized bioquantization via group theoretic approach. If you have noticed, our equation is composed of 2 integral factors. First is the Fourier transform of the function to be quantized. Second factor, U hat, is the irreducible unitary representation of the group associated to the phase space of the function f. Upon quantization, ambiguities in the ordering of operators has been noticed, since there are infinite number of possible orderings corresponding to the quantum operators. Actually, this kind of issues already exist as early as 1920s in the history of quantum mechanics. Thus, to eliminate this ambiguity, ordering rules in quantization were introduced. Ordering rule is characterized by a real-valued function, let's say k, such that when we evaluate k to 0, its value is equal to 1. If we impose ordering on the quantization process, then our equation 1, as presented earlier, will be modified. We'll look at equation number 2, which is the modification of equation 1. There is an additional integral factor k. This integral factor dictates the ordering rule of the quantization, and this formula is also patterned from the results discussed by Prasanovsky and his co-authors in some of their papers. They call it the generalized Stratonovich bioquantizer of K. But in our computation, our focus is the quantization of time of arrival functions of a particle moving on a unit circle. The variable position q can be regarded as the arc length of the circle, and q is equal to the angle, and its corresponding operator is multiplication by an angle theta. While variable momentum p is considered as the angular momentum, and And it will be denoted by capital L and this computation. And its corresponding operator is the partial derivative of the function with respect to the angle theta. Function phi of theta is an element of the Hilbert space, which is equal to L squared of S1. Now, consider the distributions on the cylinder R cross S1. From the work of Plibansky and his co-authors, it says there that function in this distribution is completely defined by the function small f. When you look at equation 5, this function has coordinates nh, bar, and theta. In our computation, we will use the same coordinates in the computation of the function time. Also, the Fourier transform of f is given by equation 6. Now, based on the coordinates that we are talking about, we have identified the group which is equal to z cross S1, and its unitary irreducible representation, u hat, is given by equation 7. So now we already established the two basic components of Weyl quantization formula. These are the Fourier transform of the function and the unitary irreducible representation of the group associated to the phase space of the function. Then, we already have the formula and quantization of time of arrival functions of a particle moving on a unit circle. If you have noticed from the formula here, it is composed of three integral factors that includes Fourier transform of the function, the integral factor k that dictates the ordering of the quantization process, and the unitary irreducible representation of the group associated to the phase space of the function. This formula 8 is our basis for quantization of the function using specific ordering. First, ordering is the symmetric ordering. This ordering is characterized by the function cosine, and we will express cosine in terms of its exponential equivalent. Using formula 8, we have achieved the quantization of the time of arrival function using symmetric ordering. Another ordering that we are interested is the Born-Jordan ordering. This ordering is characterized by the function sine, and we will express the function in terms of its exponential form again for easier computation. So the quantization of time of arrival function using Born-Jordan ordering is achieved using formula 8. We have observed from the computation that computing for the Fourier transform of the function with specific ordering actually can be realized using multiplication of the integral kernel k and the Fourier transform of the function. So equations 13 and 14 are Fourier transforms of the function with specific ordering, symmetric, and Born-Jordan. Here, we use f subscript w for the Fourier transform of the function, and w here stands for the Weyl ordering, since we know that the integral kernel for Weyl ordering is just equal to 1, which means that f subscript w is just simply the ordinary Fourier transform of the function. If we want to achieve the Fourier transform of the function with specific ordering, then we will use formula 15, where k is the integral kernel that characterizes the ordering scheme. Looking back, equation 2, which has three integral factors, we can now reduce it to two integral factors for simpler notation. So we have here the quantization formula with specific ordering. So another important observation here is that given the probability distribution associated to symmetric and Born-Jordan quantization is equal to the convolution of two functions, the Wigner function or the quasi-probability distribution associated to the state psi, and the integral kernel k that the one that we have discussed earlier. So which means For the time operators, the generalized Ratonovich-Weil quantization leads to the determination of their corresponding quasi-probability distributions and their cohen classes. Elements of this class is determined by getting the convolution between the Wigner function and the cohen kernel. In this case, our cohen kernel is the integral kernel K. That's all. Thank you.
Good day, everyone. I am Aaron Hulian, and with Vincent Munar, we studied Lie algebras twisted by fractional differential operators. Just to give you an idea on how Lie algebras arise in physics, whenever you have a physical system that follows some conservation laws, according to Noether's theorem, there's an underlying symmetry that governs these rules. These symmetries can be encoded in a Lie group, which are usually hard to study due to their algebraic nature. Hence, we turn to their associated Lie algebra in order to facilitate our calculations. A Lie algebra is a vector space frac G over some field K together with a bilinear map that satisfies Q symmetry and the Jacobi identity. This bilinear form is called the Lie bracket on frac G. To form a twisted Lie algebra, we need a commutative associative algebra A over a field K and a linear map that twists the bracket as follows. If bracket psi satisfies Q symmetry and the Jacobi identity, then the pair A bracket psi is now called a twisted Lie algebra. Bracket psi is called the psi-twisted Lie bracket. If we take A to be the algebra of smooth functions defined on R and psi to be the nth order differential operator, then we have a twisted Lie algebra whenever n is equal to 1. However, the same conclusion will not hold for higher values of n. In this paper, we want to know if we can have a twisted Lie algebra for fractional values of n between 0 and 1. By convention, we will use alpha instead of n. Here are some results regarding twisted Lie algebras. Whenever we have a commutative associative algebra A and a linear map psi, then the twisted bracket will always be skew symmetric. To check for the Jacobi identity, we just have to see if property 2 holds. A direct corollary to this is if we have a linear derivation delta, which is a linear map that satisfies the Leibniz rule, then we'll always have a twisted Lie algebra. We are now ready to present our first definition of a fractional derivative, which is according to Riemann and Liouville, given in equation 1. Okay? It was shown by Podlubny that this fractional derivative is linear as shown in equation 2a. It also follows the product formula given in 2b. Now, if we define the twisted bracket as follows, then we don't have to worry about skew symmetry due to the linearity of the Riemann-Liouville fractional derivative. We just have to check if Jacobi identity is satisfied. Now, we just have to invoke proposition 1 to get this equality. Apply the definition of the twisted bracket and apply the product formula to arrive at this expression. Notice that this will not in general be 0, hence we conclude that the Riemann-Liouville fractional derivative will not give us a twisted Lie algebra. We present our second definition according to Caputo, given in equation 3. This can be expressed in terms of the previously defined Riemann-Liouville fractional derivative and the kth order derivative of a function f. Similar to that of the Riemann-Liouville, this is linear as shown in 5a and has the product formula given in 5b. Following the same computation as that of the previous twisted bracket, we can say that the Caputo fractional derivative will not give us a twisted Lie algebra. Finally, we have the Cayley fractional derivative given in equation 6. We'll call this T alpha. Okay? It was initially defined on non-negative reals, but it can be extended to include the entire real line as its domain. Doing so, we'll notice that T alpha is linear and satisfies the Leibniz rule, which means T alpha is a linear derivation. Hence, we have a twisted Lie algebra on the algebra of smooth functions on R. One of the earlier uses of this Cayley fractional derivative is on time scales, which are closed subsets of R endowed with a subspace topology. It was shown by Benketu that the T alpha fractional derivative satisfies equation 8 whenever we're working on a timescale T. F and G here are smooth functions, while sigma is the forward jump operator defined as follows. So if we have a point on T that is sent to itself by the forward jump operator, we call that point right dense. We say that timescale is right dense if all of its points are right dense. Notice that sigma will act as if it is the identity operator, then equation 8 will be reduced to the familiar Leibniz rule, which means we'll have a twisted Lie algebra on alpha differentiable functions defined on right dense timescales. It's now natural to ask how right dense timescale look like on R, and we claim that these are nothing but the connected timescales. A timescale T is connected if it cannot be expressed as a disjoint union of its non-trivial open subsets in the subspace topology. We proceed by proving this claim, showing that connected timescales are right dense is trivial by just using the definition. In order to show that right dense timescale are connected, we will invoke proof by contraposition. Hence, we assume that we have a disconnected timescale T, which means it can be expressed as a disjoint union of closed sets U and V. Without loss of generality, let us assume that the supremum of U is less than the infimum of V. Let's label the supremum of U as small u, apply the forward jump operator on U, which will give us the infimum of V. Clearly, this will not be equal to U, hence the disconnected timescale T is not right dense. This proves the claim. In summary, the Riemann-Liouville and the Caputo definition will not give us a twisted Lie algebra, but the Khalil fractional derivative will. In particular, the Khalil twisted Lie algebras only exist on right dense timescales, which are not connected, which are the disconnected timescale, which are the connected timescales on R. A good future direction is to examine the mathematical properties of the twisted Lie algebra that we devise on timescales. It can potentially open up possibilities of studying symmetries of dynamical systems defined on timescales such as the hybrid discrete continuous dynamical systems. Here are my references. Thank you for listening.
Going to discuss to you our work entitled The Star Product of Functions in the Euclidean Motion Group. So here's the flow of my discussion. First, we're going to introduce the three pillars of phase space quantum mechanics. Phase space quantum mechanics is one formulation of quantum mechanics wherein the three pillars are, we have the Weyl transform, the Wiener function, and the star product of functions on phase space. In 1927, Weyl formulated a quantization recipe that shows how operators are assigned to functions. So here, we have a linear operator W sub sigma associated with a phase space function sigma. This linear operator is called the Weyl transform. And this Weyl transform can be mapped to a function W sub a hat called the Wiener transform. And according to Grunwald and Moyal, these two are inverse processes of each other. In 1932, Wiener introduced a quasi-probability distribution function defined on flat phase space, given by this equation, which plays the role of probability distribution in quantum theory. So he introduced this function to study quantum correction in thermodynamics equilibrium. And this function satisfies the following conditions. So we have the marginality and traciality conditions. So we can see here the relationship of Weyl transform and the Wiener function when we consider the expected values of quantum observables W sub sigma. So these expected values are computed when we get the average of the Weyl transform, which is written in terms of the Wiener function. These two pillars became the basis of what we call the Weyl-Wiener-Grunwald-Moyal formalism. So here, given two functions f and g, we can now formulate an associative non-commutative product of functions called the Grunwald-Moyal star product, defined in terms of the composition of two Weyl transforms given by these two equations. Our paper focused on the construction of star product of functions, but this time, the phase space is the Euclidean motion group in three-dimensional space, which can be viewed as a cotangent bundle on the sphere. We will be presenting also the properties of the star product of functions on E3. Let us now describe the Euclidean motion group and in particular of rank 3. So this is a six-dimensional Lie group describing the translation and rotation in three-dimensional Euclidean space. This group is important in studying quantum optics and in signal analysis. We can also write this as a semi-direct product of the translation and special orthogonal group. The elements are parameterized by small a coming from the translation group and capital A coming from the special orthogonal group. And these elements can be written as a 4 by 4 transformation matrix of this form using the exponential map. The volume element or the Haar measure of this group is given by this equation. And take note that this group is left and right invariant, and therefore this group is called a unimodular group. And because the existence of the volume element, integration in this group is now possible. So we can define the version of convolution of function on this group given by this equation. For the unitary representation of E3, the operator u raised to s sub g acting on the function f, which is a square integrable function on the sphere, is given by this equation, wherein delta is the helicity of this representation and s is a real number that counts the number of unitary irreducible representation on this group. And when we write the UIRs of E3 explicitly, this one is in terms of special functions. And we need also the concept of Fourier transform version on E3 given by this equation, which is in terms of its UIR. And the usual property of the Fourier transform also holds in this group given by this equation. We now construct the star product of functions on E3. So the basic idea is to imitate the construction of star product in the standard case, which is the composition of two Weyl operators on the Heisenberg group. So here is the definition of the Weyl operator associated to the Heisenberg group. Here we have sigma hat, which is the Fourier transform of the function sigma, and then rho represents the Schrödinger representation of the Heisenberg group. Imitating this definition, we came up with the Weyl operator associated to E3 given by this equation, wherein k hat is the Fourier transform version on E3, and we have here the UIR on E3. And when we write the Fourier transform and then the UIR explicitly, we obtain this particular equation. And the composition of two Weyl operators on E3 is given by this equation. Now, the highlighted expression, when we let this to be equal to f star L, the composition is now in terms of the function f star L. Here, f star L defines the star product of functions on E3, which is entirely analogous to the twisted convolution on the Heisenberg group. And the operator W sub f, W sub L is defined in terms of the integral factor called the kernel, and hence f star L here represents the kernel of this operator. And because f star L is the kernel of the operator W sub f, W sub L, this function inherits the property of the operator. We have shown here that the operator is bounded, and hence f star L is also bounded, which is now an element of the Schwarzschild on E3. We also showed that star is associative, linear, and satisfies the triviality condition. And we also found an identity element, which is the Dirac delta function. And to summarize our discussion, the composition of two Weyl transforms using the UIRs of E3 induces the star product of functions on this group. And the computed star product is now the version of twisted convolution on this group. And finally, the properties of star on E3 that we have presented follow the usual C star algebra properties of quantum theory. That's all. Thank you for listening.
Hi everyone, I'm Jeffrey Tale. I'm from DOST PNRI and DOST SEI. So on behalf of my co-researcher, let me share with you our work on space fractional neutron diffusion equation with race fractional derivative. So in this study, we provide a fractional order modeling of neutron transport, which we regarded as a neutron diffusion process. So why do we have to resort to fractional order modeling of neutron transport? So first, the conventional integer order model predicts infinite neutron speed, which is unphysical. So second, neutron transport in strongly absorbing media is a subdiffusion process. So subdiffusion processes or anomalous diffusion processes can be more accurately modeled by using fractional derivatives. So in this work, our main problem is to obtain an expression for the Newton flux, psi of x. So neutron flux is one of the most important quantities in nuclear reactor theory since it provides us the number of neutrons passing through a certain region of space in a reactor after some time. So we obtain expressions for the neutron flux from an infinite planar neutron source. So this is our system. So we have here our neutron source located at x equals to 0 and represented by a Dirac delta distribution with strength S naught. Our diffusing medium here, or our moderator, is light water, which is the most commonly used moderator in light water reactors. So in this study, we obtain Newton flux using two approximations, namely the one group approximation and the two group approximation. So under one group approximation, so we regarded neutrons as monoenergetic, whereas in two group approximations, we group our diffusing neutrons into two, namely the fast neutron group and the thermal neutron group. So in general, the energies of the fast neutrons are greater than the energies of the thermal neutrons. So before proceeding to the fractional formalism of the neutron diffusion equation, let me show you first the conventional time-independent neutron diffusion equation as given by this equation. So take note that the parameters here are the diffusion coefficient D, the macroscopic absorption cross-section represented by sigma A, and of course we have the Newton flux and S of x, our source function. And in this diffusion equation, we have here the presence of the 1D Laplacian operator. So in the fractional formalism, we replace the 1D Laplacian with the risk fractional derivative defined in terms of Fourier transform, such as in this equation. So our risk fractional derivative has a fractional order alpha, which has these values. So take note that when we set alpha equal to 2, this fractional differential equation reduces to the conventional Newton diffusion equation I've shown you earlier. So the quantities here, psi of x and psi wiggle of q, in this definition are related to each other by the Fourier transform. And the solution of this equation in the transform space is given by psi wiggle of Q. So if we want to recover, or if we want to obtain our expression for the neutron flux psi of x, we simply take the inverse Fourier transform of psi wiggle of Q. Okay, so under one group approximation, our space fractional neutron diffusion equation can be written in this form. So if we take the Fourier transform, we get psi wiggle of Q as our solution. And finally, taking its inverse Fourier transform, we obtain the Newton flux psi of x. It's given by these integral representations. Now, to have a closed form of this solution, we evaluate the integral in terms of Fox's h function, and our final result is given by this equation in the box. So this is the graphical representation of our solution. As you can see, the alpha is equal to 2 here represents the solutions in the non-fractional regime. And other values of alpha represents our solutions in the fractional regime. So there is a deviation of our solutions for both the fractional and non-fractional regimes. And near the vicinity of in the vicinity of the source, we take note that the values of the Newton flux tends to higher values as alpha decreases. And in this region, okay, in these regions, okay, we observe behavior akin to the subdiffusion process, but still this needs to be validated by means of, let's say, calculating the mean squared displacement. Okay. So for the two-group approximation, we have this pair of equations for the fast neutrons and thermal neutrons. Take note of uh, the difference in the source terms, as well as the use of the different macroscopic cross sections. If we solve it using Fourier transform method, we can obtain an expression for the thermal Newton flux, such as given in this result, expressed in terms of Fox's H functions, where the L parameters are termed as the groove diffusion length. Okay, for the graphical representation of the solutions, okay, take note that we obtain almost similar trends in the one group approximation. The difference is that in the vicinity of the source, the deviation of the Newton flux values between the fractional and non-fractional regimes is smaller. And also, a behavior resembling subdivision is also observed in these regions away from the source. And again, we still need to validate it, further validate it by calculating the mean squared displacement. Okay, so for the conclusions, so Newton diffusion was modeled using fractional Newton diffusion equation, Riesz fractional derivative of order alpha. The Newton flux for diffusion from an infinite planar source through light water as our diffusing medium or moderator was obtained under one group and two group approximations. And the solutions were expressed in terms of Fox's H functions. So in most regions, deviation between Newton fluxes in fractional and non-fractional regimes was noted, and it was more pronounced as alpha decreases. So the behavior resembling subdiffusion was also observed, but it needs further validation by calculating, let's say, the mean square displacement through time fractional calculations. These are my references. And finally, I would like to acknowledge the career incentive program of DOST SEI for providing support to my work at DOST PNRI. That's all. Thank you for listening.